Hi, so in this video, we are going to talk about quantum gates and particularly how they relate to universal quantum computation. So getting back to quantum states, we had earlier noted that quantum states were some point in a geometrical object called the Bloch sphere. Let me draw the Bloch sphere for you. So there is this sphere and the surface of the sphere are points which represent qubit states. So I have, let's say, a point over here, and this angle is theta, and this angle is phi. Then any qubit can be represented as a point on the Bloch sphere. So the point um, given by these angles theta and phi is this state of the qubit. So e to the I phi um, sine theta over 2 get 1. All right. So that's for quantum states. Now, what about quantum gates? How is there a way to represent them geometrically on the Bloch sphere? Indeed, there is. What happens in the case of quantum gates is that they are actually rotations about some axis of the Bloch sphere by a specific angle. So when I want to specify a rotation, I need to specify two things. I need to specify an axis. So let's say this axis or something like that. An axis can be given by a vector, a unit vector n. And then I need to specify an angle. So axis and angle, let's say alpha. So quantum states are, or sorry, quantum gates are unitaries on C2, right? So quantum states are actually e to the I theta, some phase, times a rotation about some angle alpha about an axis n on the Bloch sphere. So any quantum gate is some phase multiplied by um, uh, a rotation. So rotation about axis given by the unit vector n by angle alpha. Now, what is Rn alpha? In fact, one can show that this rotation can be given in terms of Pauli matrices. So this is can be written as e to the minus I alpha over 2 n dot sigma hat, where n is our unit vector, nx, ny, nz, and sigma hat is just the Pauli matrices x, y, and z. Now, n dot x is sort of a inner product, you can call it. N dot sigma is nx x plus ny y plus nz z. And this is a unit vector, so nx square plus ny square plus nz square is equal to 1. And because of the fact that our Pauli matrices, if I square them, x square is equal to y square is equal to z square is equal to the identity, I can write Rn hat of alpha as cos alpha over 2 identity minus I sine alpha over 2 time n hat dot sigma hat. Okay, so this can be shown by the fact that the Pauli matrix squares up to the identity. And of course, I didn't mention that this is a matrix. So this is a matrix. So when I say e to the power a matrix, this is just the expansion of identity plus a square over 2 factorial and so on, just like we define for the real numbers. And this is well defined provided a has certain properties and so on. Right. So let's take an example of the Hadamard gate. So if I have the Hadamard gate, how do I represent it by a rotation about the Bloch sphere? So I know that the Hadamard gate is this unitary 1, 1, 1 minus 1, correct? So I can decompose this. So I can write this as 1 over square root of 2, 0, 1, 1, 0 plus 1 over square root of 2, 1, 0, 0 minus 1. So it is 1 over square root of 2x plus 1 over square root of 2z. Right now, let's take a look at this this equation over here. Suppose I want this matrix, Hadamard matrix, to be defined by this equation. Suppose I take the angle alpha. So take angle alpha equal to pi over 2. So what happens? So Rn, and then let's take n to be 1 over square root of 2, 0, 1 over square root of 2. Then Rn of pi. So I'll take, no, not alpha shouldn't be pi over 2. Alpha should be pi rather. Okay, so if I take Rn of pi, then this will be cos pi over 2 identity minus I sine pi over 2. And I'll have 1 over square root of 2x plus 1 over square root of 2z. Right? Cos pi over 2 is 0. So therefore, this will get minus I. Sine pi over 2 is 1. So it will get minus I times h. So Rn of pi, where n is this vector 1 over square root of 2, 0, 1 over square root of 2 is I times h. So h will be equal to I times Rn of pi, or it will be e to the I pi over 2 into Rn of pi, where n is equal to 1 over square root of 2, 0, 1 over square root of 2. Right? So what is this rotation? So the if I look at the Bloch sphere, this is my x-axis, this is my y-axis, this is my z-axis. And in the xy plane is the vector n, right? So if I take this xy plane over here, so this plane over here that I see, there is this vector which is passing through the plane, and the rotation is by angle pi about this vector n. So n is equal to the vector which is passing through the plane x xz. There is no y component, and angle alpha is equal to pi. So you take this vector, and if I rotate it by angle pi, then you will get some phase multiplied by the Hadamard gate. So now how does this all relate to universal quantum computation? So it turns out that so let me just before you just a reminder that universal quantum computation means that if you should have a discrete set of gates, and using gates only from that set, you should be able to approximate any unitary, any single qubit unitary. So now the idea for universal quantum computation is the following. Suppose I'm able to construct any arbitrary angle about a fixed axis, okay, let's say n, and then I'm also able to construct an arbitrary rotation about another fixed non-parallel axis. So this is my axis n, and this is my axis m. So suppose I'm able to have these two rotations with me, and I'm able to do that using this discrete set, then I should be able to construct any other any rotation about any other axis. So for instance, if I have the available to me Z rotations and X rotations, then I can construct a Y rotation or any other rotation. So that's the idea of universal quantum computation. So we need to find a discrete set that can create these rotations about two non-parallel axes.